Hello, students. Today we want to discuss related rate problems. In the last lecture, we worked with the implicit technique. That is, we would work with an implicit equation in X and Y and differentiate with respect to an independent variable. Usually it was X, and we would assume that Y was a differentiable function of X and use the chain rule to keep up with Y prime, and then algebraically solve for Y prime. So that technique is extremely powerful based upon the implicit function theorem, which will continue to be used throughout the calculus sequence, and more so in calculus 3, when you have even more variables to contend with. So it, again, very, very important technique. Now with related rates, the problem is simplified somewhat. The independent variable will always be time. Time will be the independent variable, and all other variables will be dependent upon time and be assumed to be differentiable. So one thing about related rate problems is that you're never having to make any assumption about the independent variable. All variables depend on time t, and they are all considered to be differentiable. So when you differentiate, all variables get the prime from the chain rule. So in that essence, it's actually, or that discussion, it's actually simpler than some of the previous problems that we did. So let's get started. Now, the first example, I think you'll find to be useful. When you study calculus and engineering, you often utilize formulas that you learned in geometry. And again, they make a good condition for doing the implicit technique. So again, remember, when you do any type of word problem, related rate or otherwise, we make assumptions about the variables, but then we use all of the ideas that we have learned along the way. So if we need to use the Pythagorean theorem, which is extremely important and useful in related rate problems, or we need to use a formula from geometry, then we make use of that knowledge. So again, do not hesitate to use any previous knowledge or prerequisite knowledge that you have. Any type of knowledge of that sort comes in extremely handy and is expected in the calculus sequence. So now what we see, we have a spherical balloon is inflated at a rate of 900 cubic centimeters per minute. And we're asked to compute R prime when R is equal to 20 centimeters. Now, R here, we're considering that to be the radius. So we will try to use variables that make some kind of sense as to what they represent. So what we observe here is that the formula from geometry will be used. That is, volume of the sphere is 4/3 pi r cubed. Again, when we work with some of the techniques of integration, we will be able to derive this formula with the integral. So we will have other means to actually give a more rigorous development of these formulas. So that will be in the future, and you will enjoy that. Now, again, just to re-emphasize what I said before, all variables are differentiable functions of t. So we have to pay attention to the differentiation process, and then once we differentiate, we have then related the rates. And that's why we actually phrase these problems related rates. How are the rates related? Okay, so notice here, the inflation gives us the rate of change of the volume. So we can write a given V prime is just 900 cubic centimeters per minute. And also, we're given a value of R. R equals 20 centimeters. And we are to compute R prime under these conditions. So if you don't get all of the given information written down initially, do not worry about that. You can always go back to the problem and read. And if you need to do some sidebar calculations to figure out some quantity, you can do that at that time. Once you differentiate and you solve for the actual object that you need, in this case, R prime, then we can observe what we have and note what we need to actually compute before we actually fill in all of the numbers and do the computation. So now we differentiate implicitly, differentiate both sides. Now I'll formally write this down. We don't always have to do this, but I'll go ahead and do this just to remind you that we are now implicitly differentiating with respect to time. Now, I'm not using the Leibniz definition, the dt, or symbols for derivatives. You can certainly do that, but the primes give us all of the information that we need. Physicists do like the Leibniz notation, but I will use the prime notation, and feel free to use any notation that you like, but this is more than sufficient. So now B, again, we just use power rules with these and then tack on the B prime. So the derivative of B with respect to time will just be B prime. And then, of course, we have the constants, 4 pi divided by 3, or 4/3 pi. And then we just apply the power rule like we did here. We'll have 3r squared r prime. So again, the differentiation process ensues just like it did in the previous lecture, and then we solve for the given rate, just like before we were solving for y prime or y double prime. And of course, that would include the requisite algebra. But now notice the 3's absorb. So we're left with B prime equals 4 pi r squared times, and I'll put the little dot there to symbolize the multiplication. Sometimes it helps just in the logic of what we're doing. And now, of course, as we see here, we need R prime, so we can simply divide B prime by 4 pi r squared. And this gives us the relation between the rates. Now, if you notice here, we have the B prime from the given, and we actually have the R from the given. That is, we are to compute R prime when these conditions hold. So fill in the details. This implies that R prime, under these conditions, we make the substitution, 900. You can include units if you want and just let the units absorb. Centimeters cubed. And of course, the minutes come downstairs. And then downstairs, we have 4 pi r squared. And that is 20 squared centimeters squared. Now, again, if you don't want to include the units, you don't have to. They will work out, but sometimes it's good just to include them to see that the units absorb as they need to. Now, notice first, we see that the squared centimeters absorb into the cubic centimeters, leaving 1 centimeter behind. So if you like, you can just write this as centimeters squared times centimeters. and these clearly absorb. And so that will leave us with centimeters per minute, which is exactly what we need. So now, of course, we have 900. We'll work with the numbers. We have 4 pi. And then, of course, we have 20 squared, which is 400. And then, if you like, you can include the units at the end. I won't continue the fraction bar as far here. And so we have centimeters per minute. And now, of course, the 100s absorb. We can get rid of this. And then we're left with 9 divided by 16 pi. Centimeters per minute. Again, it is your choice. The units are useful. Many times when I'm doing computations with related rates, I may use them, I may not use them. It is important that the numbers be correct. And if you're using valid formulas, then of course, the units will also self-correct and absorb as needed. But I'll let you make that decision. I think when you first start, it may give you more confidence to go ahead and write them in and see how the details of the calculation give you the appropriate units. So now what we see when the instantaneous rate of change of the volume is 900 cubic centimeters per minute, and the radius is actually 20 centimeters, we see that the R prime, or the instantaneous rate of the radius, is 9 divided by, need my 16 pi centimeters per minute. So again, sometimes instead of saying just instantaneous rate, we'll just say rate. But we know with the calculus, with the derivative, it is instantaneous. That is, we have the rate at a point on the curve, so to speak. And that is occurring with these conditions here. So if I say rate, that will often mean, or also mean, instantaneous rate. So we have 9 divided by 16 pi centimeters per minute. So again, let me reiterate that many problems will deal with formulas with which you are familiar. Formulas from geometry, formulas from physics, where you will differentiate with the implicit technique, assuming the independent variable time and that all other variables that are dependent on time are actually differentiable, okay? So let's look at another one. Now, you had an example with the infinite limits that already addressed this problem, and it was a good example. And I like it because it gives some kind of indication about what's coming up down the road. And there will also be another problem that I give you that will be concerned with related rates that you can work. So again, just remember, techniques that you utilize in calculus will stay with you for the rest of your education, because as you continue in STEM, these techniques will be basically the foundation of your computational ability. This will be one that you'll use often. As I said before, the implicit technique is very powerful. So now we have a ladder that is 25 feet long. Notice I have a diagram here, leaning against the wall of a house. So again, just a very meager diagram, but gives us all the geometry we need. The base of the ladder is pulled away at 2 feet per second. Okay, so we're going to label, I'll say more about that, and then of course this will be a given condition. Consider the triangle formed by the ladder, side of the house, and ground. So we make the assumption that we have the side of the house, the ground, and the ladder, and the configuration of the right angle. So we're thinking we have good construction science here, okay? That is part of the problem in order to do it. Then it says, find the rate of change, instantaneous, as I've noted. Again, we will always assume that, of the area of the triangle when the base of the ladder is 15 feet from the house. So let's just write a little bit of the given here. Again, the length of the ladder is 25, as I've noted here. And then, of course, what we're seeing is that it says the base of the ladder is pulled away at 2 feet per second. So what we're seeing is that this distance here from the base of the ladder to the house, we call x. This will say that x prime, or the rate of change of x, will just be 2 feet per second. So we have a given x prime equals 2 feet per second. And then we think, okay, well, what we want to do is figure out something about the area, which will be easy to compute with the way we've labeled things. But that's going to require that not only do we understand the rate of change of x, but we're also going to need the rate of change of y, or y prime. So let's look and see what we have. Notice we have the Pythagorean theorem here. So first, we're going to say that 25 squared equals x squared. Now, of course, we're given for the particular area change, we're going to need x to be 15 feet. That is, the base of the ladder is 15 feet from the house. So I'm going to go ahead and write here x equals 15 feet when we need to do our calculation. So we'll have 15 squared plus y squared. So that's the Pythagorean theorem. So now, of course, if you want to look at this, notice we just go ahead and retire everything to one side. This is 25 times 25 minus, and of course, 15 is 3 times 5. So that's going to give us a 9 times a 5 times 5, or a 25, equals y squared. So just very simple numbers, but easy to manipulate. And of course, now we can factor the 25s. We'll just go ahead and box those for factoring. So this gives us 25 times 25 minus 9, which equals y squared. And so now, of course, we have, now 25 minus 9 is 16. So we have 5 squared times 4 squared equals y squared. And of course, by laws of exponents, this is just 20 squared. So if we take principal square roots, again, this would imply that our value of y will be the positive, or the principal square root, which will be 20 feet. Of course, the square root property gives the plus and minus, but relative to the problem, we just need the 20 feet. So we could say y equals plus or minus 20, and then we select, based on the problem, the positive response. So not to ignore the algebra, we simply are focusing on the value of y that makes sense relative to the problem. And so now, again, we have our value of y, but we can now use the Pythagorean relationship to get y prime. So now we have 25 squared. We could just write that as 625 if you want. I mean, it's just going to absorb to 0 when we differentiate, equals x squared plus y squared. And so now we'll go ahead and do the formal differentiation. So we have 0 equals 2x x prime plus 2y y prime. Now, of course, we can divide by the 2's, they just absorb. So we have x times x prime plus y times y prime equals 0. And then, of course, if you like, we can just go ahead and solve for y prime. So transposition, that gives us the negative x times, put a little dot there, x prime divided by y. So again, this relates the rates. We already know the rate of x, and we know x and we know y, so we can fill these in. So we have the negative of x, 15, times x prime, which is 2 feet per second, and then downstairs we just have y. If you like, let me go ahead and write in the units here since I'm doing that. Dot negative 15 feet. And then, of course, y is 20 feet. So the units work out. 2 copies of the feet absorbed, and we're left with feet per second. We have the negative, and of course, we have negative 3 times 5 times 2. And then downstairs, we just have 4. Well, I'll just go ahead and write it this way. Go ahead and factor the 4 too. 2 times 2 times a 5. And of course, we have feet per second. So now, of course, the 5's absorbed, and 2 copies of the 2's absorbed. So that leaves us with a negative 3 over 2 feet per second. And this is y prime. So many times in a problem, if something is not given, then you will be able to compute it with the given information. It's set up so that you have sufficient information to solve for the unknowns. Now, again, you can include the units in your computation, just like you factor the numbers to compute. And again, I look at that as just being more expansive in your work. And of course, in a physics or an engineering class, you would be expected to include units. But again, I think the first time you go through it, it's probably good to utilize the units to get some additional practice. Now let's finish the problem. Notice that the calculations here give us all the information that we're going to need. Before I move to the next page, let me just go ahead and write down the formula for the area. That is, we now have this right triangle. So we have base times height times 1/2. So we will define area to be 1/2 x times y. And then we can fill in the details. I'll probably have enough room here. I was just thinking that I didn't have enough room, but we'll see what we can fill in. So now upon this definition, let's differentiate. Then I'll move to the next paper. So I'll go ahead and write this out formally, the differentiation process. You don't have to always do this, but as you do it for the first time, just remind yourself that you're differentiating the equation with an implicit technique. So prime. Now we can move to the new sheet. So what we see, we have the derivative of A with respect to T. So that just gives us A prime, like B, the derivative of B with respect to D, with respect to time just gives us B prime. So the same calculation. And then, of course, we have the constant here, and then we have to apply the product rule. So we have 1/2, and then we have xy prime. So by the product rule, we have 1/2. So x prime times y plus x times y prime. Again, we're just applying the power rule, but it's like differentiating x relative to x. You just get one, and then you're left with the derivative. So by the chain rule, we have 1x prime times y, and then we have x, 1y, y prime, or 1 times y prime. So again, think of this like differentiating the variable, the power function to the first power. Remember, we had that isolated case of differentiating x and just getting 1 relative to x. So when we just got the single variable to the first power, the result is just the a prime. The x just gives us the x prime. The y just gives us the y prime. So think about the differentiation process of power functions, and you won't slip up with this. And now we have the rate that we need here. We just need to fill in the details. So this implies that a prime for all of the given, and again, let's just go ahead and summarize all of the given on the sheet so you can see it. We have x equal to 15 feet. We have y equal to 20 feet. That way you don't have to write all of this down relative to the rate here. Just kind of summarize it to the side. We have x prime equal to 2 feet per second. And then we have y prime equal to negative 3/2 feet per second. So let's fill all of this in. So we have 1/2. So we have x prime 2 feet per second. And then y is 20 feet plus x is 15 feet. And then, of course, y prime is negative 3/2 feet per second. Again, very simple arithmetic. But notice now we get the feet squared per second. So we have area units per unit time, which is exactly what we need. So we can move that off to the right and retire the units from our calculation. So notice first, we just have 2 times a 20, which is a 40. We could factor, but we're okay with that. So we have 40. And then, of course, here we've got a 15 times a negative 3, which gives us a negative 45 divided by 2. And then, of course, this is squared feet per second. So now we can just get a common denominator. So we have 2, and of course an 80 minus a 45 square feet per second. So 1/2, or actually just go ahead and multiply. We have the 1/4, and then of course the 45 from the 80 is 35. So we get 35 over 4 square feet per second. Now again, the time that you take to summarize, that is, when you start the problem, to write down the given, compute items that you need for the calculation. Now, of course, if you don't think that you need this calculation, you can go ahead and compute the rate of change. And then when you look at the rate of change, you may find yourself, okay, well, I need y prime, so go back and do that computation. But once you look at the actual rate that you need to compute, you can see from the relation of the rates, how the rates are related as to what variables that you need. And of course, we have all of these, and we just summarize them here. Sometimes it's better to do that than to try to say this is a function of all of these values here. It gets a little bit long-winded. So maybe to summarize what you need and then fill this in And then the given rate for these conditions is this, 35/4 square feet per second, okay? So that's a nice application of the implicit technique. And as you practice with this, you will find that it reminds you of the previous section, but now everything gets a prime. Just remember, with the implicit technique, we have to establish what is differentiable, what is the composition, and all variables in the related rate problems are differentiable functions of t. So we have to apply the derivative of the inner function in all of these variables. So that's why everything gets a prime. So that is the difference, but I think it makes it maybe just a little bit easier. Now, the next one, we want to continue with the ladder. And what I've done here in red, I've just written everything that we remembered from the last calculation. You know, we often just know when problems have several parts, they're often lower parts, or, you know, part C may be dependent on parts A and parts B. So what I've done here is just write previous work and all of the details that we had from the last part. And what we have here, it says, find the rate at which the angle between the ladder and the wall is changing when the ladder is 15 feet from the wall. Well, that's really good for us, because we know that when we've got the 15 feet here and we've got the rate of change of X, we get the rate of change of Y. And so all of this is now good based upon this. So the problems are connected via these numbers. So you don't have to start over, which is good. We know X prime is given in the problem, but we don't have to compute a new value of Y, and we don't have to compute a new value of Y prime. So this is the key, that we have the same number here. So just remember that often it will be the case that the parts that follow later in the problem will be dependent upon the previous parts. So now what you notice here is that the angle is made by the ladder and the wall of the house. So this introduces right angle trigonometry. Now, students often say, well, what trig function do I use? And I'll say, you choose. The consistency of mathematics is beyond reproach. If you apply a consistent method, then the response that you get is valid. You just have to say, I'm using this function, so I must differentiate it with the formulas that I know. So do not worry when you're working with a problem, especially in physics. There might be certain conventions that are utilized for certain types of calculations, but you are certainly not required to use any specific type of function. Usually what happens is we just use the simplest possible combination that is available to us. So notice here, we need, in this case, the angle. So we want to compute, let's just write this down, compute theta prime, because we're just going to call it theta or any Greek letter you like, with these given conditions. So with these conditions, what is the rate of change of the angle here that's formed by the ladder and the wall of the house as this is sliding away? Okay, so again, it's like you take a snapshot. You're taking a snapshot, it's instantaneous rate of change. And so we have to understand that the limiting process is not something we can always, you know, envision. It's like it's in motion, but boom, at that point, you know, at that instant in time, that's when we want the calculation. So what we can do is just a very simple, if you like, opposite over adjacent. So if you like, this just implies that tangent theta equals the opposite side over the adjacent, like that. So that, we'll just say this is easy. Use any trig function you like, it doesn't matter. You know that this is a 25, so if you wanted to use a sine or a cosine, you could do that too. So you have plenty of flexibility here. I just chose this as an option just for something interesting. So now let me formally write, and I'll go ahead and put the 25 in here. And then as specific values here, if you like, we can go ahead and say 15. Of course, I'm not using the units here, and the 20 if we need some separate calculations down the road, okay? So that's the snapshot right there. So tangent of theta prime equals x over y prime. Again, use whatever trig function you like, but I think it's interesting just to utilize the tangent function. So now we differentiate. So the derivative of the tangent function is secant squared. So we have secant squared theta, and I'll put a dot here, times the derivative of theta via the chain rule. And now we use the quotient rule on the other side. So we have the derivative of x, which is x prime, times y, minus x times the derivative of y, which is y prime, divided by the square of the denominator, which is y squared. So that is the differentiation process. So now all we have to do is isolate the theta prime. So if and only if theta prime equals x prime y minus x y prime divided by y squared, and I'll just put a little dot here, secant squared. So that will numerically, that will give us what we're looking for. And what we can notice here is that we're not solving this except in pure measures. So we're going to have radians per unit time. And that's what's interesting about this particular problem. The units do work out, but we have to let them fall out of the problem. Now notice here, we've got the x prime, we've got the y, we've got the x, we've got the y prime, all of that's covered. And we need the secant because we need to square it. So now you can just go over to the triangle and take the snapshot here and observe. So we'll add this to our given, observe. And this really depends on how we choose the trig function here as to what's going to come out here. So secant, again, that relative to theta is, what is that? We think cosine is adjacent over hypotenuse. So now we need hypotenuse over adjacent, which is the reciprocal. So we have secant theta equals hypotenuse over adjacent. So the 5's absorb, and that gives us 5 over 4. So this is another given piece of information here. So what we see here is that this actually simplifies very nicely. So let's go ahead and fill in the details. So we have x prime 2 feet per second, 2 feet per second, times y, which is 20 feet, minus, we have x, 15 feet, and then y prime, we have negative 3/2 feet per second. And then we divide by what? Y squared, which is 20 squared. So 20 squared times, and of course, this would be, I'll go ahead and put the feet squared here, kind of cheated a little there. And then, of course, the pure number, 5 over 4 squared. So that would be what? 25 over 16. Pure number. Okay, so now notice our units work out very nicely. The feet squareds, they all absorb with the feet squared downstairs. So the feet squareds absorb. And we're left with pure number per unit time. The second just collapses to the denominator. So we've got our units of pure number per unit time. So we now have established that, and we can just move that to the right in our calculation. So now if you look at this, and we can do the same type of calculation before. We've got a 40. And then we have, of course, minus, so this is plus. We have a 45 over 2. So 45 over 2, the negatives absorb. We have a 40 here. And then now, if you like, we can reciprocate. The 16 can come upstairs. And then downstairs, we have 20 squared, which we can write as a 400, or 20 times 20, times a 25. So now let's go ahead and simplify some of this. Notice we have a 2 here, so we just, if you like, we can get a common denominator. We have an 80. So we have an 80 plus 45 over 2 times the 16. And then, of course, we have 20. And if you like, we can go ahead, let's go ahead and break that down a little bit. We've got that, of course, the 2 would absorb into the 16, but let's go ahead and get rid of it. That'll be a 4 times a 5 times a 4 times a 5 times a 25. So let's go ahead and get that absorbed. And of course, this is per real number per second. So let me just say 1 over second, not to forget the units. So the 4's absorb with the 16. So we'll move the calculation to a new sheet. So now, if you will, if we look at this, let's go ahead and bring the 2 downstairs. So we have the 125 upstairs from the 80 plus the 45. So we've got equals 125. And then downstairs, of course, we have the new copy of 2. So we have 2 times the 5 times, again, we've got another 5 here. Let me write that in. And then we have the 25. And this is 1 over second. Those are our units. So now, of course, the 125, that's just 5 times 25. So let's go ahead and factor that. And of course, we've got the 25 here and the 5, so we'll write that to the side. They will absorb. And then, of course, the 2 times the 5 is just a 10. And then the units 1 over this reciprocal seconds. And then, of course, the 5 and the 25 absorb. So we basically write the numbers relative to the factoring that we've done, and that way it's actually easier. And then we're left with 1 over 10 reciprocal seconds. So I could just say second minus 1. So sometimes we just say radians per second. So the snapshot says that the angle between the ladder and the wall at these given conditions here, that snapshot, the instantaneous rate of change is 1/10 radian per second. Now, you see the power of this technique. You see the power of this technique by the assumption of the implicit function. And this opens a whole new door to calculations that were not earlier available to us. So you see the power of this technique. It's extremely powerful. And so we want to make good use of this. And I think the related rate problems really do highlight the fact of the major use of this technique. And so it's a very elegant process and something that you can use to refine your techniques for physics class. So very nice problem. Okay. Now, I've got a problem here, I think, that turns up in every calculus course, and maybe it's not the most popular problem, but it is a very time-tested problem. And it's certainly not very difficult, but it sounds difficult. The problems we've done previous to this are more complicated. So this one's very simple by use of similar triangles. And so it seems, again, difficult, but when you actually organize the details, assuming again, good construction science, the problem is very, very straightforward. And again, seems easier than it should be. But sometimes in calculus, the simplicity of the solution is what is difficult to us. So we have a man 6 feet tall, walks at a rate of 7 feet per second. Pretty fast. That's pretty fast. Maybe this is, not very realistic. Away from a light that is 15 feet above the ground. So I've got the stick figure in the light, which is up here, okay? The 15 feet, so we can think of that as a pole, and the light's right up here. So if you want to do a little shiny thing for the light, you can, whatever. Now then it says, when he is 10 feet from the base of the light, at what rate is the length of his shadow moving? So you've got, the way I've arranged this is that, of course, as the light is cast, the shadow is here. And so I've used S for shadow, and then just the distance from the light or the base of the light, I just call that X. So when we look at this, we see the length of the shadow moving. We're looking for S prime. So in this case, for part A, compute S prime. Again, remember this is based upon the letters that I've chosen here, and this is certainly not unique, so you can use whatever letters you want. But now what we can see is we assume good construction science, and we have a right angle here and a right angle here. So we've got a smaller triangle, which is similar to the larger triangle, and that is the key behind this. And again, if we want to use some of the given, this is what we want to compute. We know we've got this. We don't really have to write that down. The height of the gentleman is 6. The light is 15 feet above the ground. But notice that walks away at 7 feet per second. So X is changing, or X prime is 7 feet per second. So we can go ahead and write that down as a given. Given. Now, again, we're trying to find S prime. We know 6 and 15. So those are given, but they're just sides of triangles. So we're okay if we don't actually write these over here, because I'm not really assigning any variable status to these since they're fixed. So again, by similar triangles, we get just a relationship between the actual X and S. So we'll say the this leg here, 15 is to 6 of the two respective triangles. Again, as X plus S is to S. X plus S is to S. Okay? So that's just using ratios of corresponding sides of similar triangles are equal. Okay, that's all that is. That's an elegant theorem and not simple to prove. You should consider looking at that. That is a theorem that most secondary teachers have to utilize in a senior level course on more advanced Euclidean geometry. The Euclidean geometry in the advanced mode is very beautiful and very challenging. Just like topology or analysis, or just like taking the calculus. We assume that theorem, but it is no lightweight to prove rigorously. So now we can go ahead and reduce some of this. Of course, we have a 2 times a 3. So this is what a 5 times a 3 and a 2 times a 3 equals x plus s divided by s. And of course, the 3's absorbed. So now, if you like, we can just go ahead and cross multiply just to make the process look a little easier. So we're going to have a 5 times an s equals 2x plus 2s. 2x plus 2s, just proportion, okay? And now just combine like terms. So this is really simple. So we have what, 3s equals, in this case, 2x. I mean, how simple is that? Now we can differentiate. So differentiate. So formally, what we do is we do 3. Now, of course, you could retire all the constants to one side. There's nothing special about what I'm doing. 3s prime equals 2x prime. So we have 3s prime equals 2x prime. It's so simple, it's deceiving. So now, equivalently, s prime is equal to 2/3 x prime. Okay. And now all we have to do is substitute the value for x prime. So with the given conditions, we go back up here, and this is the main condition we have, is the rate at which the gentleman is walking away from the light. So we have s prime is just equal to 2/3 times the rate, 7 feet per second. And that gives us 14 feet, or 14 over 3 feet per second. Again, 14, 3 downstairs. And that's so it's clear. There we go. So 14/3 feet per second is the rate at which the length of the shadow is changing. Now, it's always good to do this one first, because we need this in the next part. And sorry about that, the 3 looks a little unclear, so let me write it so you can actually see it. There we go. That looks a little better. So now, part B just says, when he is 10 feet from the base of the light, at what rate is the tip of his shadow moving? So basically, we want to see how this entire distance is changing relative to time. So x plus s prime is what we need. And you're thinking we kind of had that over here, but not quite. So in this case, let's just write, we want to, again, all the same conditions, compute, so we don't really have to work on anything new, compute x plus s prime, because we want to see how this entire distance moves. As this tip changes, that is how these are changing, how the sum of x and s are changing. And so by linearity, we're covered. So that's what we need to compute. So this is very simple. So now this implies, of course, once we do this, we've done the hard part, which you see is not very difficult. So x plus s prime by linearity is just x prime plus s prime. And so we just fill everything in. X prime we know is 7 feet per second. And we just computed s prime, which is 14/3 feet per second. It's so simple, again, deceiving. So now we'll just get a common denominator of 3. So we have what? 21 plus 14 over 3 feet per second. And of course, we have a 5, so that's a 35 over 3 feet per second. So that is the rate at which the tip of in this case, when we call it, the tip of his shadow is moving right here. So again, it's how this whole distance is changing. So actually, when you think about the problem, it's more of a play just on how we verbalize it. So again, the tip here is changing as the sum of these is changing. And then, of course, the first question was to say, how is the length of the shadow changing? So the tip moves relative to x plus s. And of course, the shadow length changing is just s prime. So again, when you work a problem like this, sometimes you may find yourself switching the orders so that they actually make sense. But the problem is deceptive. Like I said before, it's very simple to state, but seems somewhat complicated. So you just make the assumption of, as I say, good construction science, where you have right angles and similar triangles. And then of course, if you notice, you're thinking, why have I not used the 10 feet? Well, there's no reason for it. And I didn't ignore it because I was being sloppy. You see the 10 feet here, and you see the 10 feet here. But it doesn't matter. It doesn't matter how far he is away from the base of the light. These are all consistent. They're constant. They don't change relative to his distance from the light, which is somewhat unique about this problem. And of course, it probably would be a neat physics assignment to test this. I mean, if you have good equipment and all, but it is relatively interesting. And I think if you look in any calculus book, you see this problem. It's a staple. And again, not intentionally ignoring this, you're probably thinking, well, why didn't you ever mention the 10 feet when you were doing the given, the snapshot and all that, thinking of that, but we don't need it. So often there will be numbers that are floating around in a problem. And I don't think it's so much to trip you up, but is to make you think about the fact that this could be another number, okay, that 5 feet away from the base, or 2 feet, or 7 feet. So a very interesting problem as you work this out with the law of similar triangles. So enjoy this problem. It's an interesting one. So now the last example that I have here, again, just remember, if you're given formulas in a problem, you use those formulas. Or if you have a problem that requires a geometric formula, you use it and make the assumption about the differentiability of the variables relative to time t. So again, you can use any facts or knowledge that you have found in prerequisite classes. As you've noticed, the calculus challenges you on very many levels. You use pretty much everything that you had learned up until this point. When you think about number theory, general mathematics, geometry, algebra, trigonometry, more advanced algebra, the conic sections, sequences. I mean, everything is present in the calculus. So it is certainly a far-reaching discipline. So when we look here, we have a baseball diamond. I've done a little diagram here to kind of relate to what is being said in the problem, so we have a point where we can start. It has the shape of a square. That is, the baseball diamond is this square. It's like the rhombus, right? 90 feet on the side. A player is running from second base to third base at a speed of 24 feet per second, okay? He is 28 feet from third base. So that's kind of like a given. So if we want to write here, if you will, and I did a little calculation here, I think that I'm going to actually need. So here we've got, let's see, x prime. Let me write given. X prime will now be 24 feet per second. And I've noted the X here when in this particular case, X is 28, X equal 28 feet. So that's going to be the snapshot. So a player is running from second base to third base at this speed, 24 feet per second. That's what X prime will be. And he is 28 feet from third base. Okay, so we're thinking of this as a snapshot. Then it says, at what rate is the player's distance from home plate changing? Okay, now what I did is I just drew the hypotenuse basically of the right triangle here and called it S and did my right angle here. And S will be this, just be the distance to home plate. So what we want to do is compute S prime under these conditions. Now you're thinking, where is that coming from? Well, let's just kind of look and see where we're going to need some of this stuff. Notice now when we look at the configuration here, this gives us the relationship, the Pythagorean theorem between S and X. So this implies, and then we'll figure out what else we need to know. S squared equals X squared plus 90 squared. So that's the relationship between S, X, and 90. So if you like, we can go ahead and differentiate. So I'll formally differentiate. S squared prime equals X squared plus 90 squared prime. So we can apply the implicit technique. So we get 2S S prime equals, again, the linearity, the derivative of the 90 squared is just 0. So we get 2x x prime. So now the 2's absorbed. And so now we can solve for S prime. So this is fairly straightforward, but interesting. So we have X times X prime divided by S. So this gives us a relationship between the rates, the relation of the rates. And so the snapshot is when we have the 28 feet. So that's where we need to do a calculation. So now here's our sidebar. So we have, in this case, S squared equals, in this case, X is 28. So we have 28 squared plus 90 squared. Now, when you look at this, you're thinking, okay, well, we need to figure out what S is, so we can use a little bit of algebra here. Notice again that the snapshot is what allows us to do this, and then I think there's some reason why I actually wrote this, and I'll get back to it. Let me check something over here that I had written down. Yeah, we'll get to it. It does make sense. I'm not really sure why I wrote that before, but I did. So let's go ahead and factor this. Notice here that we've got what? We've got a 2 times a 14. So that gives us a 28. And then plus, we've got 90. That's just a 2 times a 45. So we have, in this case, 2 times 45. And that's squared. So that's exactly where that came from. Now this is making sense. So now this equals, so if you will, we've got the 2 squared and the 2 squared. So that's a 4 times 14 squared plus 45 squared. Okay, and so that's where this is. I went ahead and wrote the 14 squared here, which is 196. So we have 4 times 196. And then, of course, the 45 squared, we just wrote as 40 plus 5 quantity squared and get 2025. So this gives us 4 And then now if we add this, okay, we get what? We've got a 1 here. And then we carry a 1, so we get a 2. And then we carry another 1, we get a 2. And then, of course, the 2 at the end. So interesting there, 2,221. And you can do the sieve of Eratosthenes on this number. That looks familiar. I do a lot of projects, honors projects with college algebra students, and a very popular project is the sieve of Eratosthenes or Eratosthenes, however you want to say it. That's a prime number, and it's not hard to prove that. And so now this is S squared. So this implies that S will just plus or minus this. So we will select the positive square root, select positive square root. So we have S is just 2 times the square root. Of course, square root of 4 is 2, 2,221. So that's another part of the given, okay? So that was the calculation we needed to do. Kind of like the y prime in the second problem. So now it looks like we've got everything we need. So this is now part of the given. So let's go back to our problem. I'll write it down here. S prime, and we're doing this at the snapshot, is just x times x prime divided by 2 times the square root of 2, 2, 2, 1. So we just want to fill all this stuff in. So x in this case is 28. So we have 28 feet. And then x prime in this particular case. And now this is an interesting deal here. Notice, and this is very important. Now you can see that we have to utilize some arithmetic here. Notice, and this is not something that we have done yet. That is, the derivative will apply a certain arithmetic. So shapes of functions with the second derivative, increasing, decreasing the first derivative. Notice that the distance x relative to time is getting smaller. So when we look at the rate here, we must include that decreasing of rate with a negative. And that's not something we've formally done yet with the derivative, but at least in terms of the increasing, decreasing that we understand at this point, this rate actually decreases. That is, as time advances, the value of x gets smaller. And so that must be realized with the negative here. So I have to go back and fix that. I mean, we have this, but relative to the diagram we have here, x is getting smaller with time, and we realize that with the additive inverse of 24 feet per second. So that's very important. So again, the given will change relative to the geometry of the situation. Fascinating, right? So now of course, that makes a big difference. So now we have what? Negative 24 feet per second. Lots of times when you initially think about something, you've got a number and you just assign it to a variable, but then you have to think about how does that particular variable change magnitude-wise? Is it getting smaller or is it getting larger? So we would think of a positive rate of change as something getting larger, a negative rate of change is something getting smaller. And that's very important, but it's not something we just make up as convention. The arithmetic of the derivative basically supports that, and it's something that we have to abide by or our numbers are incorrect. And so now, of course, we have 2 times the square root of 2, 2, 2, 1. And of course, this is a distance, so this is feet. So now everything's going to absorb the way it needs to. We have 2 copies of the feet absorbing. So now we're going to have feet per second, which we need. So of course, we'll retire those units to the right because we're done with them. Now, of course, we can absorb the 2 here. If you want, we'll just have what? 2 times a 14, of course, there's a negative now, times a 24, so we'll just say 20 plus a 4. And then we have 2 square root 2, 2, 2, 1. And of course, the 2's absorbed. So now this will give us a negative. So if we look at this, this won't be hard to compute. So we have a 0, and then we have a 2 times a 4, which is an 8, and then a 2 times a 1, which is a 2. And then now we just hit that with a 4. So 4 times a 4, that's a 16, and a 1, we get a 56. And of course, the 2's absorbed. So we have what? 2, 2, 2, 1. And then when we add, we get what? We've got a negative. So we've got a 6, and then we've got a 13, and then a 1. So a negative 336 divided by square root of 2, 2, 2, 1. And I've been a little bit sloppy here, put in the feet per second. We should just carry those along since we bothered to compute them. And I make the point about retiring it to the right, and of course I leave it out. So we have feet per second, excuse me, and then feet per second. So now the distance, and if we go back to the original problem, the distance from the person running the snapshot to home plate is changing at this rate. And of course, that distance is getting smaller because as the player proceeds to third base, this distance is getting smaller, clearly. And so if we don't have the correct sign here, then the problem is off. So when you're doing your related rate problems, do think this way. If the geometry of the situation is showing that a particular variable is getting smaller relative to time as time progresses, then that rate must contain a negative sign. If it's getting larger, then it is what it is. So when I initially wrote this, I just put the 24 feet per second and assigned it to the variable x and left it alone. But then as we come back to it, it's clear that particular variable relative to time is getting smaller. And so now, of course, this makes sense because we now see, at least relative to the geometry, that the distance from the player to home plate as time progresses is also getting smaller. So we don't want to remove that thought process from our argument. As we move on in the course, as we get into more theoretical aspects of the derivative, we will see that the arithmetic supports exactly what we're doing. And so sometimes it might be good to talk about that before, but the related rate problem is so intimately tied to the implicit differentiation technique, it makes sense to cover that and then to set up the geometry and the intuition that supports the negatives that we need in certain rates of change. So again, think of the intuition and the geometry as assigning a particular sign, as you will, to the rate of change, whereas a positive sign or no negative means an increasing rate of change, and the negative, a decreasing rate of change. So this again is not a surprise. And as you work through the problems, if you find that you have an issue with sign, go back to the geometry and check what the situation is and assign the correct value in terms of the pluses and the minuses. So I think you'll find that as you do these types of problems, they will remind you really quite a bit of your physics classes when you think about kinematics. And now what you can see is that if we have related rate problems, the calculus is perfectly suited to the physics. And of course, I'm just beating something that is clearly true. The mathematics that we have, the calculus, is the foundation and the language of physics, and therefore the language of engineering. And so when you study STEM, you are just intimately connected to the calculus, even in computer science, even in finance, in the medical arts. Math is everywhere. So enjoy these related rate problems. And then as we transition into the next chapter, we will discuss more theory of continuity, more theory of the derivative that will allow us to do new things. That is, we want to be able to look at functions from a standpoint of optimization, because that is an essential tool in the calculus. And then once we exhaust all of that, and we're pretty much tired of the derivative, or at least what we can do with it for now, we'll reach into the next topic, which will be the antiderivative and the Riemann sum. So enjoy these problems, and we'll see you next time.